We use pH to indicate how acidic or basic a solution is. Lower pHs, lower than 7, means you have an acidic material. Higher than 7 is basic, also known as alkaline. And in the middle, pH 7, we call that neutral. So we'll refer to acidic substances based off its pH. If you have a very, very low pH, people know that to be acidic. And people can use pH paper and stuff like that. What sometimes gets forgotten is pH is actually a measurement. And what we're measuring is how strongly acidic or weakly acidic a material is and in aqueous water-based conditions. And this is referring to how much protons, H+, is freely available in the solution. So let's describe that and let's get on to calculations. So when we talk about proton availability, you'll see for most of the video we're going to be writing stuff like H+, or the concentration of H+ in molarity, which is put in brackets. But to be technical, we're actually referring to a hydronium ion. Here, let me spell that for you. Hydronium, and here's a hydroxide. All right. And what we're looking at is something called autoionization. All right. This is the very small, we're talking 1 in 10 million here, the very small likelihood of finding water, 2 water molecules actually, having split into ions at any given point in time. Most of the time, these ions will revert back to being 2 different H2O molecules, but every once in a while, you'll have 2 water molecules combine, or react, excuse me. And what happens is this water right here will take this proton off of this other water molecule, and that'll leave a hydroxide ion. All right. As this water snatches off the H, it leaves the electrons behind that were in that bond. So that's why hydroxide ends up with a negative charge. And then this water here ends up with a positive charge because it stole just a hydrogen and its plus charge without any electrons. All right. And so we have a hydronium ion. That's where the hydrogen came from. And I think it's worth knowing that technically speaking, but in reality, what people do most of the time is they'll just refer to this hydronium as H+, because it's easier to think about acids in that way. So here's the main event, our pH equation sheet. In my mind, there are 6 equations you should memorize when it comes to calculating pHs. That may seem pretty intimidating, but I think it's a common expectation in a 101 curriculum to be able to calculate your own pH from scratch. So I think we'll try to commit these to memory. I will show some tricks to simplify this process. You can see that there's some symmetry. For example, these two basically are identical to these two, except here everything is in terms of H+, whereas everything here is in terms of OH minus. So mirror images, that helps. And these two look similar to each other. There's a 14 there, there's a 14 there. All right, and depending on your math background, you may realize that these two are actually mathematically identical statements. Same with these two, and same with these two. So I'll show that right now. If you're not interested in that mathematics behind the scenes, then feel free to skip that little chapter of this video. But otherwise, here it is. So we take the first statement, pH equals to negative log of H+. All right. So you'll notice that the H is the same on both sides. We just don't write the plus in pH. That would sound weird. No one says pH+. That's the same, and so the only difference between the sides is P is right there, and then we have negative log right there. So P is a symbol meaning negative log of something. Okay, and this is a log base 10. All right, if you don't know what a log base 10 is, that's probably fine for today. On a standard calculator, the log button is right there or something. It's going to say log. That means log base 10. If your calculator doesn't have any other offerings, it's log base 10, and you're good to go. If you've heard of a natural log based off of a base of Euler's number, sometimes mispronounced Euler's number, E-U-L-E-R, that's not what we're talking about. We're not talking about natural logarithms. Log. Okay? So that's what the P means. So it's a negative log scale. All right, so that means as your concentration gets higher, your pH numbers will actually get lower. That's one of those things you think about it. That's kind of weird, actually, but that's the way it is. All right, but back to deriving the equations. So I wanted to prove that these two are actually the same statement. So let's do some algebraic manipulation. We're just going to change sides here first. Let's move that negative over there. Looks like I need a new line. All right. Now, these are log base 10s, and the way you cancel out a log is by having everything become the exponent of that base. So in other words, we're going to say 10 to the power of log base 10 h plus, and we're going to have to do that to both sides. Okay, so that's the exponent for 10. This becomes the exponent for 10. So the 10 and the log base 10 cancel, leaving you with H plus concentration, and this is in molarity. Anything in brackets means molarities, moles per liter, is equal to 10 negative pH, parentheses if you like them, as promised. Sweet. And then same argument for POH. All right, how about for KW? All right, this statement and that statement are the same thing, was my argument. So we can do something similar here. 10 to the minus 14 equals H plus OH minus. If we do a log base 10 on both sides, log of that, then that will cancel, and then that will leave us with a negative 14 there. These can split. Now, the reason why I put a negative there is because the definition of P is negative log of something. So I had to go out of my way to put a negative sign on each side. Kind of weird. But hey, those negatives all cancel, so everything is nice. Okay. All right, and there's probably more than one way to do these derivations. Math allows for whatever creativity you want, so long as if you're in the world of correct mathematics. But yeah, that's my way of drilling in the equations into my mind. But yeah, the number 14 features very highly when we're talking about pHs. Okay, speaking of pHs, here's the next part. This is really important. How do we think about pH? So 7 is neutral. Anything lower than 7 is acidic. That means your H plus concentration is higher than your OH minus concentration. And then basic, aka alkaline, comes from having, you have a higher pH, higher than 7, and that comes from having more hydroxide than protons. All right. So that's the pH scale. Okay, I wrote it in a simplified version here. Now there is something called the POH scale. In the POH scale, you are measuring off of the hydroxide, which has the exact opposite behavior of H+. So in other words, the numbers lower than 7 are basic, and the numbers higher than 7 are acidic. If you're comfortable thinking in either pHs or pOHs, great. But for most students, and heck, for myself, I really recommend not caring about that. I mean, maybe don't totally delete it in your head, but maybe keep it just more in the back of your head than the front of your head. For me, I am so comfortable with pH that even if I know I have a basic solution and I have a pOH measurement on it or something, I will go out of my way to change it to a pH number because I am so used to pH. Maybe that's my biggest tip of the day. I don't know. A few other things worth noting. Again, H plus means the same thing as H3O plus. And then mathematically, a change of pH by 1 is equal to a 10 times change. It's a log scale based off of 10, right? Whereas a pH of 2 is 10 to the second power, meaning it's a 100 times change. Okay, so that's the power of a log scale. And then if you're interested in the mathematics behind the scenes, here it is. Again, pH plus pOH equals 14. And so you can see 0 plus 14 is 14. You know, we can go like 4 plus 10 is 14. 7 plus 7, this is neutral, is equal to 14. 14 plus 0, this would be very, very basic, equals 14. That holds true. And notice with the H plus and the OH minuses, the powers of 10 always add up to being a negative 14 every time. And we proved earlier that the mathematics of the concentrations are related to those of the P numbers. All right. So yeah, that's the pH scale. I think we're ready to do some calculations. Maybe one last interesting comment is pHs below 0 are possible. That's where you have like strong acids, or if you're like way below 0, you might even have some super acids or something like that. All right, but no super acids today. We're going to do everyday examples people can relate with. All right, before we start, I know this slide looks pretty busy, but basically what we can say is most of what we do in Chem 101 deals with strong acids and strong bases. And so there is a nice simplification we can do, okay? If you have a strong acid, that means 100% dissociation. So that means you have something like hydrochloric acid, that's your most stereotypical strong acid. It's going to fully ionize into H3O plus and Cl minus ions. So here's the shortcut that makes things way easier with strong acids. Whoops. Whatever your HCl concentration is, it's the same as your H3O plus concentration. And we like to just simplify that to writing H plus. So basically with a strong acid, if they gave you the concentration of hydrochloric acid, just know that that's the same as your acid concentration itself. The same thing also goes with strong bases. Whatever your strong base concentration is, that is the concentration of your hydroxide as well. Since I know one person might ask this, what if you have something like H2SO4? That's a strong acid, right, Josh? This shortcut applies to the first proton, but it actually does not apply for the second proton. After the first proton is released, the second one has a harder time being released. And at that point, the second proton is something you would call a weak acid. And the weak acids do not work with this 100% dissociation assumption. All right. And the same might be true for like bases. The first one's good. The second one might also be good, but it might depend on the base you're dealing with. So I think that's just not necessarily a safe assumption. But I do know there's chemistry curriculums out there that will tell you that you'll get like 2 hydroxide from this because there's a 2 there. So if that's the case, if that's what your teacher says for you to assume, then just go with that assumption. All right, with all the little disclaimers and whatever's out of the way, we can finally get to the fun part of calculating. All right, example 1. So we got some hydrochloric acid solution. It's prepared to a concentration of 1.00 molar. Calculate the pH of this solution. Okay, so if you're in a class where they provide you a menu of equations, go ahead and choose the right one. If you're required to memorize, then what I advise my students to do is just write out all the equations like before you get your exam. Just do your equation dump and then choose the right one. All right, so they want a pH and they give us an H+. So this is plug and chug. Okay, strong acid, we can just use this directly. I guess in the calculator they usually have the brackets as a parentheses. All right, so this is what you put into the calculator. Make sure there's no glare. Okay, good. Negative log 1.00 if you want it. Close the parentheses, hit equals. We get 0. Okay, we get a pH of 0. So this is a very, very strongly acidic solution. Okay, for my students, I would be okay with this. But if you're in a class where they ask you about sig figs in your pH calculations, there's something you might want to be aware of. All right, here's a nice web page from CHEM LibreText. Looks like this was put together from Anoka Ramsey, Community College. Thank you to them. So let's take a look. We have a nice example here, H3O plus at a bunch of different concentrations, but they're actually not that different. So making sure I'm pointing at the mic here. If you look at examples A and B, these are very similar H3O plus concentrations, 5.6 times 10 to the minus 5 versus 5.7 times 10 to the minus 5. Now you look at how those pHs calculate out. You can see that for the 5.6 one, we get 4.25, and then for the 5.7 solution, we get 4.24. So you can see when those pHs are being calculated, they only differ in the hundredths place rather than in like the tenths place, which maybe is what you would predict from the original number. And that's because we're dealing with like a base 10 scale, and so that means the uncertain digit gets moved to a different spot. So the long story short is this. In our problem, we would do this. Okay. So if your concentrations, this is for sig figs, go to, here we have boink, 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 boink. That means our pH will go boink, 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 boink. All right, so in other words, pH has 1 more sig fig than concentration. Okay, so we went 2 decimal places out there, so this would be 3 decimal places out there. Okay, so this would be our answer. You may wonder, can you have sig figs on 0? Yeah, you can. It depends on how far out the 0 is, and it is that far out, so that's totally fine. All right. Example 2, let's do more of an applied example. Let's talk stomach acid. Stomach acid, you have, protons being released. You have chloride being released in the stomach. And so you make HCl, hydrochloric acid. And in someone's stomach, that can be between like a pH of 1 to 3. So let's say someone's stomach acid had their pH measured at 2.01. Let's calculate the concentration of H3O plus, aka H plus, in this person's stomach. Let's go to our menu of equations again. We need the H plus. Let's plug in the pH. .01. 10 to the power of, I think there's a fancy button for that in a calculator somewhere. Yeah. Oh, it's the opposite of log. I mean, duh, as it should be. But if you don't have that, you can just do 10 caret negative 2.01. Does my calculator need parentheses? I don't know. I'll just do that. All right, 0.00977. Okay. And we go 1 sig fig less on the concentrations. Again, if it was my students, like 101, I don't care about sig figs. You can just write that. I wouldn't really care, but there you go. Since it is a concentration in molarity, let's put the M for molarity there. All right, if they ask for a scientific notation, oops, one more. 9.8 times 10 to the minus 3 molarity if they wanted scientific. Okay. Example 3. Let's do something a little different. What is the pH of, now here's the curveball, I gave sodium hydroxide as the reagent rather than, what do you call it, an acid. I gave a base here instead. Okay, so we can go back to our menu of equations. So we have an OH concentration right now. Okay, here's the route I like. We can actually use this equation, plug into OH minus concentration here, the negative log of it, we'll get a POH. And then to get the pH, we'll subtract that answer out from 14. I like that. So we're going to do OH minus to a POH value first. All right, so this is strong base, we just used that. 0.00123 molarity. All right, if you're getting a syntax error, remember many calculators require you to hit a negative button rather than a subtraction operation. Log 0.00123. Close that. And we get 2.9. One zero, because pH goes one digit more. I wish I'd chosen concentrations to only 2 sig figs, but too late, we're already recording. Because pH is often, on like a pH probe, for example, will often go only like 2 decimal places out. Whatever. All right, that's our POH, but that's not what they asked for. They asked for a pH, right? So we're going to turn our POH into a pH. And so the equation goes 14.00, and it's 14 exactly, so like you can give yourself more zeros if you need it. Yeah. Maybe I should have just wrote 14 exact. It's the end of the semester almost. I'm starting to second guess things more and more. 14.00, so that's going to be equal to pH plus POH. So we'll just subtract the POH from both sides. .910. .09. That's significant, so we'll keep the 0. And that's our pH, 11.090. Makes sense. I mean, we have a basic solution from adding a base, so it should be a pH above 7, and it is. All right, last example for the day. This is a question that sometimes you'll get on a homework or exam. They'll give you like a pH or something, one of these 4 values, and then they'll ask you to calculate the rest of the values, and then maybe they'll just have you give a remark on the conditions of this aqueous solution. That's probably the easiest thing to do. We have a pH of 7.38. That's above 7, so it's basic. They gave the pH, so we can just plug that into the table right now. All right, the low-hanging fruit to me feels like the POH. So we can just do POH equals 14.00 minus 7.38. That feels like 6.62 maybe. Yeah. All right, put that in. All right, and then next up, oh, my bad. I'm not going to edit that out. People are waiting on this video, so my bad if that gives you motion sickness. So H plus, yeah, we need to do this one. All right, 10 to the negative 7.38. Oh man, that is some crazy, well. All right, that's 10 to the minus 8. And the concentrations are supposed to be 1 sig fig less. So 4.2 times 10 to the minus 8 molarity. Let's just double check that though. I'm going to use a scientific engineering switch button. I'm going to go to scientific mode. 4.168 blah blah blah. That was behind the scenes. Oh, no one can see that. Here, I'll do that one more time. Wait. 10 caret negative 7.38. Looks like it didn't need parentheses. Scientific. Yeah, so that was the result, but we're only supposed to go to 1 sig fig, or 1 decimal place anyways, if our pHs had 2 decimal places. Okay. Might as well stay in scientific mode there. So we're almost done. .2 times 10 to the minus 8 molarity. At this point, we have 2 choices. We could solve for hydroxide in this equation right here, or we could plug in the POH into this equation. I am perfectly comfortable with either one. I suspect most people will want to do this one. But for the sake of example, I'm going to show that this, I'm just going to do it both ways. I'll let you decide after I do it both ways. So the first way would be OH minus 10 to the minus POH. All right, so 10 to the 6.62 negative. All right, and we get 2.4 times 10 to the minus 7 molarity. All right, and then I can show the other way of doing it. OH minus is equal to the auto-ionization constant of water, which is 10 to the minus 14 molarity squared. Sometimes, you know, I should have done this earlier. Some people like to write it this way. With a 1.0 in front. That's kind of a good reminder in hindsight that concentrations often go to just one decimal place, if I could have gone back in time. All right, and that's going to be divided by the H plus concentration. I just did the algebraic rearrangement of this. Okay, through the H plus to the denominator there. All right, so now I'll have to use parentheses for the denominator here if I'm going to type into one line on this calculator. The alternate would be dealing with the powers of 10 separately. What was my H plus constant? Oh yeah, 4.2 times 10 to the minus 8. All right, from a unit point of view, we have molarity squared over molarity, canceling the square and the molarity into a single molarity. Anywho, let's type this into the calculator. Might need a different ring light. This glare is crazy. Okay. And yeah, we get the same answer. So checks out. Okay. And there is our info table. A way you can check your work on these is you can multiply these two together and you should get this auto-ionization constant of 1.0 times 10 to the minus 14 within rounding error, within reasonable rounding error. And then if you add up the pH and the POH, it should equal to 14. All right, but that's how you calculate pHs and whatnot. Let me know if you have any questions or comments. Otherwise, have a great day.